5.1 is about differentiation with the natural log. So in order to work with the natural log and differentiation, we need a little bit of background information, and then we're actually going to use the definition of derivative to derive the derivative of natural log of x. So first, let's just talk about logarithms. Logarithms came about as a necessity. They came about because oftentimes in science fields, in math fields, in all kinds of different areas, we're talking about numbers that are really, really large or numbers that are really, really tiny. And a logarithm came about as a way to talk about those numbers in a way that makes sense. Typically, in a normal logarithm, we're talking about things in terms of base 10, and in many math classes, it makes sense to talk about a log of base 10. In calculus, as I mentioned in the 5.0 video, in calculus, the only base that actually means anything at all in calculus, the only base we care about, is the natural log, which is a log base e, and E refers to Euler's number. Yes, even though it looks like it says Euler, that man's name is pronounced Euler. So Euler's number E. And when we talk about E, it makes sense to talk about E when we're talking about natural log because they are inverses of each other. So the way that natural log is defined in calculus helps fill a hole or a void that we have, an error that we have when we have the power rule. What I mean by that is right now, if we tried to integrate 1 over x dx, what would happen? So according to the power rule, well, this is the same thing as x to the negative first power. So according to the power rule, I would add 1 to the exponent, which would give me 0. So I would have x to the power of 0, and I would multiply by the reciprocal. So I'm multiplying by 1 over 0 plus c. So this is obviously an issue. This is something that we can't manage based on what we currently know. So the power rule doesn't work here. So what mathematicians actually did was they looked at the area under the curve of 1 over x from 1 to some value a. So you can literally, and we will in class, graph this function 1 over the integral from 1 to a of 1 over x dx. And what they noticed through just analyzing and error and test analysis was what they actually noticed is that graph, the integral from 1 to a of 1 over x dx, that graph was actually identical to the graph of natural log of a. And since we can replace a with any given variable or number, we could come up with that natural log of x is equal to the integral from 1 to x of 1 over t dt. So based on the second fundamental theorem of calculus, we can integrate both sides of that, and we can get that we can differentiate that on both sides, so we can get that the derivative of natural log of x is 1 over x. So part of this idea came from the fact that we were looking at the area under the curve of 1 over x, or 1 over t dt, and analyzing that and finding the comparison between functions. So one thing I want to point out is that the derivative of natural log, that has a domain restriction that x has to be greater than or equal to 0. Sorry, it has to be greater than 0 for natural log. This has a domain restriction that x is just not allowed to be 0. So since these domains aren't the same, the way that we accommodate for that is that we include absolute value when we are dealing with natural log in integration to basically encompass both of those domains at the same time. So that is used with integration. But I feel like I haven't really proven to you the derivative of natural log, and this whole section is supposed to be about differentiation with natural log. So let's briefly do a proof of the derivative of natural log. So we're going to find the derivative of natural log of x. And spoilers, we know that this is going to be 1 over x, and knowing that kind of helps direct or take the direction of our proof. So right now, and there are multiple ways to prove this, but I want to prove this without using anything really but the definition of derivative. So by the definition of derivative, this is equal to the limit as delta x approaches 0, or as h approaches 0, I'm going to use delta x in this case, of the natural log of delta x plus x minus the natural log of x all over delta x. So we can use that fact, and then now that we're talking about how do I simplify this, right? I can't use direct substitution here. I'm going to get 0 in the denominator. So how could I simplify this? Well, let's just start by using simple properties of logs. So the limit as delta x approaches 0, and I'm going to just pull 1 over delta x to the front so I have a little bit more space. I can condense these two natural logs when I'm dealing with logarithmic properties. Subtraction means division, so I could rewrite this as natural log of delta x plus x over x. And then I'm actually going to use two properties now. I'm going to simplify this fraction, natural log of delta x over x plus x over x, which is just 1. The second thing I'm going to use is I'm going to use the fact that this number in front, based on properties of logs, I can just rewrite that up here as an exponent, right? I can pull that forward using properties of logs. Now, the next thing I'm going to do is I want to, in some way, kind of simplify all these delta x's. So I'm going to let n equal delta x over x, which means in here I'm going to have n plus 1. I'm still going to have natural log here. I'm still going to have a limit. Note that as delta x approaches 0, delta x approaches 0, n is also going to approach 0, so I'm going to change this to be as n approaches 0. And then 1 over delta x, so actually let's take this and multiply both sides by x, so that's going to give me n times x equals delta x, and I can take the reciprocal of both sides, and this is also the same thing as breaking this into two separate terms. So that means my new exponent here is going to be 1 over n times 1 over x. And again, based on these rules of logs, we can actually take this 1 over x, which, spoilers, we know that that's what the final answer is going to be, but we could actually take this 1 over x and we can move it to the front by properties of exponents. And if you think about 1 over x, as n approaches 0, that's not affecting 1 over x because there is no n there. So what I'm going to do is I'm going to rewrite this as 1 over x times the limit as n approaches 0 of natural log of n plus 1 all to the power of 1 over n. I'm going to rewrite this one more time, because natural log is not actually changing, right? The thing that's changing as n approaches 0 is this n plus 1 to the power of n. And I'm taking the natural log of that. So I'm going to actually rewrite this limit on the inside, which is fine because I'm still going to take the natural log of whatever that limit is, n plus 1 to the 1 over n. So this right here, and this is not something I would expect you to know, but this is a proof, right? So I'm going to tell you, this is actually a definition of E. This is one way that E is commonly defined. The limit as n approaches 0 of n plus 1 to the power of 1 over n. Because of that, as n goes to 0, that is what I am just going to get, natural log of E. And what is natural log of E? Natural log of E is 1, which means that the derivative of natural log of x is 1 over x. So there is a more formalized proof than just talking about the graph in general and what has been discovered over the years. I wanted to show you a more concrete proof of where that comes from. So now that we know that the derivative of natural log is 1 over x and that the integral of 1 over x is natural log, we can use that to take derivatives of functions involving natural log. So let's focus on some practice now. Every math class that you have been taking has really been leading up to this class. So when you're working through problems with logarithms, remember the things that you learned in Algebra 2, those properties of logs. They are going to make your life easier here. So I have natural log of 3x squared, but using properties of logs, I can simplify that to be natural log of 3 plus 2 natural log of x. This then makes it so much easier to take the derivative. So the derivative of natural log of 3, that's the derivative of a constant, that's going to be 0. The derivative of 2 natural log of x, well, the derivative of natural log of x is 1 over x. So this is going to be 2 over x. Similarly, on number 2, this is really the same thing as 4 of natural log of 4 plus 2 natural log of x minus natural log of x minus 1. I just totally cut into this problem. That's okay. So now when I take the derivative, dy dx, this constant is going to become 0. This is going to become 2 over x. This is going to become minus 1 over x minus 1. The derivative of x minus 1 is just 1. So that's why we still just have a 1 in this numerator. So why don't you go ahead and pause the video and see if you can work through the rest of these on your own. So on number 3, I can rewrite that as natural log of 3 plus 2 natural log of t minus 5t. When I take the derivative, the constant goes away. I get 2 over t minus 5. X, natural log of x, we're going to need to use the product rule here. So dy dx is going to be the derivative of x is 1, so natural log of x, plus x times the derivative of natural log of x, which is 1 over x. So this is really going to be natural log of x plus 1. For number 3, we're going to have to use the chain rule because we have a function within a function. So the derivative of natural log is 1 over the thing inside. So 1 over cosine of x times the derivative of cosine of x, which is negative sine of x. You could absolutely leave this answer just like this. You could also simplify this. This is going to be negative sine over cosine, which is just negative tangent of x. But again, it's fine for you to leave it as negative sine over cosine as well. Similarly, on number 6, to take the derivative of the outside function is going to be 1 over cosine of x times the derivative of the inside function, which is, 1 over sine of x, times the derivative of the inside, which is cosine of x. You could leave this as cosine over sine, or you could write this as cotangent of x. Number 7, we're going to have to use the quotient rule here. So the derivative of the numerator is going to be 1 over x plus 1. So this is g prime of x. 1 over x plus 1 times the denominator, x squared, minus, keep the numerator the same, multiply by the derivative of the denominator, all over x squared squared, or x to the 4th. You can leave it like this. You could also factor out 1 over x to the 4th, which might make it a little bit easier to look at, but you're more than welcome to leave it just like this. And then number 8, we haven't talked about how to deal with a variable in the variable, which should be an indicator that I have to do something to change this function so that I actually can find the derivative of it. So this is natural log of 3 plus x natural log of x. Now we can take the derivative. dy dx is going to be, that's a constant, so 1. Then the product rule, natural log of x plus x times 1 over x, or natural log of x plus 1. So we have talked about how logarithms of a base that's not e, or anything besides natural log basically, is not something that we're going to use in calculus. However, that doesn't mean that it's not something that you might see on a particular problem. So we need to talk about how, or we need to remind ourselves, how do we take a regular log that's not a natural log and convert it to a natural log? So just as a reminder, and we did this in the 5.0 video, you can change something like log base b of x to be natural log of x over natural log of b. Those are equivalent statements by the change of base formula, which you established in Algebra 2. So now let's look at, if we know then that instead of taking the derivative of natural or log base b of x, we're taking the derivative of natural log of x over natural log of b. A couple things I want to remind you. Natural log of b, if we're taking the derivative with respect to x, this is just a constant. So what we're really doing is multiplying 1 over natural log of b times the derivative of natural log of x, which is just 1 over x. So that's how we get this right here, 1 over x natural log of b. So let's work through some examples where we have logarithms that are of a different base. Remember, use your properties of logs to expand as much as possible, then convert from log log to natural log. So here I could expand this to, this is the same thing as y equals log base 3 of x plus 1/2 for that square root times log base 3 of x plus 1 minus log base 3 of 2. To convert that to natural logs, we're going to take 1 over the natural log of the base. And what is the base of all these logarithms? That base is 3. So 1 over the natural log of 3 times, and then I'm going to substitute in natural log for all of my log base 3's. 1/2 natural log of x plus 1 minus natural log of 2. Now we can take the derivative, so dy dx is going to be equal to 1 over natural log of 3 times the natural log of x derivative is 1 over x. 1/2 natural log of x plus 1 is going to be 1 over 2 times x plus 1. Natural log of 2 is just going to go to 0 when I take the derivative, so I can just stop right here. All right, for number 10, let's start by converting this to natural log. So this is log and there's no subscript, which means this is going to be 1 over natural log of 10 times natural log of x squared plus 3x minus 5. So to take the derivative of that, I'm going to just leave my 1 over natural log of 10 in front. This is going to be 1 over the inside part of the function, so 1 over x squared plus 3x minus 5. But in the numerator, we need to apply the chain rule here, so we need to take the derivative of what is in the denominator, which is going to be 2x plus 3. You could simplify this to be one fraction. I'm fine with you leaving it just like this. So remember that the chain rule still applies. If the thing that you're taking the natural log of has a derivative other than 1, that needs to go into the numerator of your fraction. All right, and number 11, let's start by rewriting this. This is going to be y equals 1 over natural log of 14 times, I'm going to move the exponent, negative 14 natural log of x. Then we can take the derivative, so dy dx is going to be negative 14 over natural log of 14 times x. And we are done. The last thing we're going to look at in this section is we're going to talk about logarithmic differentiation. We're going to do a few examples on that, and then we're going to just wrap up with a couple of other examples that tie multiple sections from previous units together. So we learned how to find the derivative of a polynomial where we have a variable to the power of an integer or a rational number, but we haven't talked about what actually happens if the variable is in the exponent. So if you see this example here, it says y equals x to the power of x. How do we do that? So thinking back, how do we get a variable out of an exponent? Thinking back to Algebra 2, what we do is we change forms. So what we're going to do here is we're going to take y equals x to the power of x, and we're going to take the natural log of both sides. So I haven't taken the derivative yet. I'm going to leave that there. But this is going to become natural log of y is equal to, by the power rule, x natural log of x. Now let's use implicit differentiation to actually differentiate here. So this is going to be 1 over y times dy dx equals, I'm going to have to use the product rule over here. So this is going to give me natural log of x plus x over x, which is just, I'm going to just erase that. X over x is just going to be 1. I'm going to solve for dy dx. So dy dx equals y times natural log of x plus 1. Except typically we're going to want this in terms of one variable, but we know what y is equal to. Y is equal to x to the power of x, so I can just change this to be x to the power of x. So dy dx equals x to the power of x times natural log of x plus 1. something I want you to notice, the fact that we ended up plugging back in our original function for y, that's going to happen on every problem that's set up like this, where we have y equals some sort of exponential function, because the very first thing we're going to do on all these problems is take the natural log of both sides, which then means we're going to have 1 over y dy dx, and we're going to have to multiply both sides by y and then substitute that function back in. So this purple part is basically going to happen on every single problem of this format. So let's look at number 12. Let's first take the natural log of both sides. Now we can differentiate with respect to x. So we're going to have 1 over y dy dx equals product rule here, so natural log of x minus 2 plus x over x minus 2. To solve for dy dx, we're going to multiply both sides by y. And then to get this as an explicit equation, we're going to substitute in for y what we know y to be. So this is going to be x minus 2 to the power of x times natural log of x minus 2 plus x over x minus 2. Similarly, on number 13, we're going to natural log both sides. That's going to give us this. We're going to take the derivative with respect to x of both sides. So 1 over y dy dx equals, and we're going to do the product rule again, the derivative of cosine is negative sine of x times natural log of x plus cosine of x over x. I'm going to do both moving y to the other side and substituting back in what y is equal to at the same time here. So this derivative, dy dx, is going to be equal to x cosine of x times, oh no, this is not going to fit, negative sine of x natural log x plus cosine x over x. I apologize. That's what I get for writing so big on number 12. Okay, for these last three problems, 14, 15, and 16, what I want to do is just kind of refresh some skills from previous chapters now using what we know about natural log. So 14 says, find the equation of the tangent line to that implicit function at the point 0, 1. So the very first thing we need to do is we need to take the derivative with respect to x. So that's going to give me 2x minus 1 over x plus 1, that's the derivative of natural log, equals 2y dy dx minus 0. So if I solve for dy dx, I get 1 over 2y times 2x minus 1 over x plus 1. We are evaluating this, so this is the slope of our tangent line, but we're evaluating this specifically at the point 0, 1. And when we do that, so dy dx, dy dx evaluated at 0, 1 is going to be negative 1/2. So then using point slope form, y minus 1 equals negative 1/2 times x minus 0, or negative 1/2 x. Okay, number 15, find the domain, extrema, and points of inflection for the graph of the function f of x equals x minus natural log of x. So something to notice, right now, our domain of this original function should be that x is greater than 0, since natural log can't have a 0 or a negative number substituted in. But let's do the math to sort of justify this here. Let's take the derivative first. The derivative of x is 1. The derivative of natural log is 1 over x. So when we're finding our critical numbers, something to note, 0 is not a critical number here because 0 wasn't in the domain to begin with. So 0 is not a critical number, so we can't ask ourselves what's making this undefined. We can only ask ourselves what's making this derivative 0, and that would be 1. So 0 was a candidate, but we can't use 0 because it was not in the domain of the original function. When we make our number line, we do need to consider 0 because we can't plug anything in that's below 0. So if I substitute in some things, this is my f prime number line, between 0 and 1, I'm going to get a negative number. Sorry, that looks like a double prime. F prime If I plug something in greater than 1, I get a positive number. So there is a relative min when x equals 1, since f prime changes from negative to positive. And if I wanted to find that actual ordered pair, that would be what? 1, comma, if I plug in 1, I get 1 minus natural log of 1. And then the second, or the last part of this question asks for points of inflection, so we need to look at the second derivative. I'm going to try and squeeze that in. So f double prime of x would just be 1 over x squared. This second derivative is only undefined at x equals 0, which again is not in the domain, so there is no inflection points, since there is no change in behavior in the second derivative. All right, let's look at the very last question. Use logarithmic differentiation to find the derivative. So the very first thing I'm going to do is I'm going to leave the d dx in front, and I'm going to take the natural log of both sides. So the natural log of y equals 3x squared minus 1 natural log of 5. To get that variable out of the exponent, I'm going to natural log both sides. Now I'm going to take the derivative with respect to x. So this is going to be 1 over y dy dx equals. Now remember that natural log of 5 is just a constant, so I'm really just taking the derivative of 3x squared minus 1, which is going to be 6x. And then the constant is just going to come along, or the scalar is just going to come along for the ride. Sorry, not the constant. The scalar of natural log of 5 is just going to stick around. So I'm going to multiply both sides by y, but I'm going to resubstitute in what y is equal to. Y is equal to 5 to the power of 3x squared, not cubed, squared minus 1, multiplied by what was already on the right-hand side, 6x natural log of 5. So key things in this section: the derivative of natural log of x is 1 over x. Make sure when you are using problems involving logs that you're using properties of logs to expand or condense in a way that makes it easier for you to differentiate or integrate. Typically that's going to be using expanding properties. Make sure that you know how to use the change of base formula if you're given a logarithm that's not a natural log. And make sure that you understand how to deal with implicit differentiation involving 1 over y dy dx, where you have to actually natural log, like we just did in this last problem, both sides for starts. Looking forward to supporting you on this material in class. Thanks for listening.